Welcome to The Explainer. Today, we're stepping into a slightly gritty cybernetic frontier. We're exploring this absolutely fascinating intersection where biological neuroscience collides head-on with the architecture of artificial general intelligence. We're going to map out an end-to-end cognitive loop that mirrors the human brain, pulling directly from the groundbreaking USDF trilogy papers. Those papers detail the Universal Signal Decomposition Framework, or USDF, and its tri-frequency cognitive routing. So get ready, because we are completely rethinking how machines perceive reality. Let's just jump right in and shatter the illusion that our brains process information the same way current brute force AI does. To quote the research directly here, biological intelligence does not push all data through a singular computational meat grinder. I love that phrasing. It's elegant, it's specialized, and it's highly dynamic. The human brain doesn't just jam everything it sees, hears, or feels through one massive uniform processing unit, which, let's be honest, sounds pretty messy anyway. And yet, that is exactly what our most advanced artificial neural networks are currently doing. Section 1. The brute force AI problem. So let's introduce the villain of our story, the rigid, monolithic architectures of contemporary AI scaling laws. The contrast between these two paradigms is practically night and day. Contemporary AI, think massive vision transformers or large language models, forces literally every piece of incoming data to optimize for a single objective. It's a uniform, monolithic approach. But biological AI, it relies entirely on specialized routing. When stimuli hit a mammalian brain, that information is instantly parsed and routed to distinct, highly structured frequency regimes. Our minds juggle reactive reflexes, short-term memory, and long-term planning all at exactly the same time, using completely different cognitive pathways for different types of data. Section 2. Biology's answer, the router. How exactly does biology solve this uniform processing problem? Well, it happens the exact moment light hits the retina or a sound wave hits the eardrum, utilizing an immediate sensory reflex. And this brilliantly illustrates the cybernetic schematic we're analyzing today. It's a four-stage end-to-end cognitive loop. First, this sensory input is intercepted by a diagnostic router. Second, that router chooses a learning strategy. Third, the data gets partitioned into distinct frequency bands within the USDF latent space, kind of like separating a really complex song into distinct bass, mid, and treble tracks. And finally, fourth, it moves up into higher-order cognitive processing. This is an end-to-end pipeline, moving from raw, thoughtless reflex all the way up to complex, deliberative planning. Let's actually zero in on that first stage for a second. When raw, unlabeled data enters the system, it bypasses deep network processing entirely. Instead, the diagnostic router acts like an early sensory reflex arc. In mere milliseconds, it calculates four computationally cheap, raw physical fingerprints: spectral kurtosis, dominant peak count, envelope peak to RMS ratio, and envelope kurtosis. In simple terms, it's measuring the spikiness, the smoothness, and the basic physical texture of a signal. It doesn't even know what the stimulus is. It just measures how it physically behaves. Is it broadband noise? Is it a sharp, isolated transient spike? By extracting these fingerprints, the system completely solves the AI cold start problem, and it does it without needing any human-labeled data. Section 3. The diagnostic recipe book. Once the system has those physical fingerprints, it has to dynamically choose a perception strategy. Now, instead of forcing one objective onto all data, which, again, is the massive flaw of the AI meat grinder, the router selects from these 5 specialized recipes. If the signal has a highly peaked spectrum, it routes to a spectral reconstruction recipe. If it detects distinct clustered categories, it routes to a mixture of Gaussians prior, which is basically a statistical sorter for grouped data. The system perfectly matches the learning objective to the physical reality of the incoming signal. It's like a bespoke learning pathway for every unique type of data. Section 4. Tri-frequency cognitive processing. So, the router has chosen the recipe, and the signal has been partitioned into 5 distinct regions. What happens next? The data moves upward into the FGSGR cognitive layer. Just like mammalian cortical brainwaves, the system organizes information across this beautiful tri-frequency cognitive symphony. Down at the bottom, operating in literal milliseconds, you have the gamma tier for reactive high-entropy feature binding. That's essentially the rapid stitching together of chaotic sensory details. In the middle, the alpha/beta tier maintains working memory over a span of seconds. And right at the top, the theta tier uses slow, stable representations for deliberative top-down planning and episodic memory. Information just flows dynamically up and down these bands. You might be wondering, how do you keep these distinct frequencies from just bleeding into a mess? Governance. The researchers added a governance structure called metanodes to coordinate the bands. And this is fascinating. Empirical testing confirmed this biological system operates best with exactly 2 metanodes. M equals 2. If you add more, performance doesn't actually improve. This proves a huge structural commitment. Cognitive governance absolutely must be minimal but present. Think of it like a really light touch orchestra conductor. They give just enough guidance to keep the strings and brass in sync, but it's minimal enough to let the individual instruments play their specialized parts without being absorbed by a central processor. Section 5. Scaling Dimensions, the Trilogy. Up to this point, the framework was characterized on one-dimensional signals, like audio or basic sensory waves. The narrative tension driving the culminating USDF trilogy papers is obvious. Is this sleek, brain-inspired framework trapped working only on simple 1D data? Well, on that 1D signal testing, this unlabeled, rule-based router performed magnificently. It recovered an astonishing 95% of the performance you would get if you had meticulously, manually tuned the system. 95%, purely unsupervised. But the USDF trilogy papers push even further. When applied to 2D images, the entire pipeline successfully transfers. They extracted 2D fingerprints, applied 2D routing rules, and the unlabeled router recovered 93.2% of the ceiling performance. And finally, punch in the 3D voxel grid data. The router hit a 94.3% recovery rate on complex 3D volumes. This is a profound finding. It literally proves that this biological methodology, fingerprinting the physics of a signal and routing it to a specialized cognitive recipe, is entirely dimension independent. The specific recipes might change, but the core architecture of biological routing scales seamlessly across the dimensions of reality. Section 6. The Biological AI Future. Now, it's one thing to achieve high numbers on synthetic benchmark data, but let's ground this in reality by exploring the ultimate test, real-world medical data. The crucial point here is that this cybernetic architecture isn't just theory anymore. It has real, life-saving potential. When researchers fed real, unlabeled medical imaging through the router, the system automatically identified the optimal learning pathways. It produced massive leaps in accuracy, a 7.9-point lift in diagnosing breast cancer imagery, an unbelievable 41.9-point lift on pneumonia classifications, and a 13.6-point lift over chance when parsing 3D blood vessel structures. It read the physical signature of the medical data and dynamically built the absolute perfect cognitive representation for it. We are no longer limited to the brute force meat grinder of the past. We now have a legitimate blueprint for an AI that reflexively feels the physics of its environment and orchestrates thought across different frequencies of time, exactly like we do. It leaves us with this really provocative, neon-lit question staring back at us from the horizon. If artificial intelligence can finally perceive and route data like a biological mind, what will it reason about next? Thank you so much for exploring this fascinating framework with me. Keep wondering, keep learning, and I'll catch you in the next explainer.